All right, so what we're going to talk about is ionic bonding. And the first thing we want to do is to review a little bit about orbital notation. Well, that's kind of review. That's going to be on the test that you're going to have on Monday and Tuesday. So that part, at least, reviewing that part is good for you to have for the test. Let me see. I'm looking for how to present so I can show you my document camera. All right. So you're going to need your periodic table, and you're going to need something to take notes with, okay? So some paper to write on and your periodic table, okay? One of the things you learned or should have learned in the first unit was regions of the periodic table. And to learn about ionic bonding, we first need to talk about where the metals and nonmetals are. Now, you may have learned about ionic bonding with metals and nonmetals combining in physical science. We'll expand beyond that. We'll actually go to what are called polyatomic ions. We'll discuss that later. We're going to start with ionic bonding as it applies to metals and nonmetals. So if you look at the periodic table here, then this black line right here, this darker line on that periodic table that I gave you, that separates metals from nonmetals. So from here over here, except for hydrogen, these are all considered metals. Now, when we were talking about sp, d, and f sublevel regions, we said helium best belongs over here. But now when we're talking about metals and nonmetals, hydrogen best belongs over here. Okay, so the periodic table is a wonderful tool. It's the most important tool that chemists have, but it's not, there's no way to lay it out perfectly. Nature doesn't work the way we'd like it to work out, so we have to know what those exceptions are. And for SPD, and F sublevel regions, and for orbital notation and electron configurations, helium best belongs over here next to hydrogen. But when we're talking about metals and nonmetals, hydrogen best belongs over here next to helium on top of fluorine. Okay? Now, if you aren't taking notes on that and you won't remember that tomorrow, that you should be that should be a lesson to you. You need to take notes on that, okay? I shouldn't have to tell you every time what to take notes on. You've got to remember. I want you to get in the habit of doing this, because when you get to college and the professor doesn't say, take notes on this, you know, you're not completely lost and fail the first test or something, and that happens a lot. I'm trying to teach you and help you learn, build skills, and the more you do it now, the more you will remember it when you get to college. And so I'm trying to help you to get to that point, okay? So when I repeat something over and over again, that's a really good clue. We talked about that in one of my classes yesterday. In college, a professor will often repeat something, and that's a really good clue that you should be writing that down. If it's something that sounds important and you don't know it, you don't remember it, then you should be writing it down. It's not just, you know, the professor or the teacher, in my case, you know, just spouting off something for the sake of spouting it off. It's something that's supposed to help you. That's why I repeat it, okay? Anyway, metals are going to be over here. Nonmetals are going to be over here. Hydrogen really belongs with the nonmetals. And we still have to know about orbital notation. So let's start with something kind of simple. We're going to choose lithium to start with. And lithium is in that metal section, okay? So I'm going to write out the orbital notation for lithium. You should do that with me, okay? So lithium is in the second row of the periodic table. We call that a period, okay, second period. So the electrons for hydrogen and helium, we're talking about sp, d, and f sublevel regions here. Hydrogen belongs here. It's in the s sublevel region. The electrons for hydrogen and helium are in that s sublevel, in that first primary energy level of the atom. We know it's in that first primary energy level because we're in the first row or first period of the periodic table. So just to remind you, we have, if this were a nucleus and we were illustrating where the primary energy levels, that would be the first energy level, okay? And they can have up to 2 electrons there. And then you have a second primary energy level. There are sublevels within that. You can have up to 8 electrons there. And that's all we need for this, but since I'm illustrating this, let me go on and show you the third primary energy level. It can have up to 18 electrons. I'm just going to write 18 E negative. The symbol E negative stands for an electron because an electron starts with the letter E, but also that negative symbol tells you the charge is a negative, okay? In the fourth energy level, and all the levels past that, you can have up to 32 electrons. And so forth. So that's 1, 2, 3, 4, 5, 6. We only need a seventh one. And I really probably, maybe I shouldn't have put 32 there, because when you get to this level, yeah, you start, some of the sublevels you can't fill up anymore until you get to a higher level, and we don't have those. So maybe I should be saying that this is 18, and this would be 8. Okay. All right. So theoretically you can have 32, but in a practical sense, in the ground state, that's what we're talking about here, you actually only have 18 in the 6th level and 8 in the 7th level. Okay. All right. So the orbital notation for lithium, we're going to fill up that first energy level and the sublevel. That's 1s. Those are those 2 electrons right here. Okay. And then for lithium, we need to be in the second period, the second primary energy level. That would be this level right here. Okay. You know, I see a lot of people's, they got pictures on the screen, but no faces. And I guess I should have thought about this before this class, but I wondered last time if people were just having their camera on and turning, they joined the class, but they weren't really in the class. So if I don't have any evidence that you're actually here, I'm not sure I should be giving you credit for actually being here, because I don't want to be talking to myself here, for the one thing. And I know that you guys sometimes get up and you don't want to get ready like you would be for school, but I got to know you're there. So if you got to turn your camera on, and you can point at the ceiling if you want to, and if I ask you to show yourself, then you got to wave your hand or something on the camera so I can see that you're actually there. Okay? So turn your camera on, wave at me. You can turn your camera up, you can turn your computer screen away from you, but I've got to be able to have some way to know that you're actually there and you're not just trying to, you know, fool me. Okay? Got it? You don't have to show your face if you don't want to. If that's uncomfortable for you, that's good. And Ben, you don't have to turn your microphone on if you don't want to. I just need to know that you're there, okay? So I heard you say something, you're good, and I see a bunch of ceilings, and that's all okay, all right? But I need you, leave your camera on there, Ben, okay? Just so that I know that you're there, and then if I ask you to wave at me, everybody can wave at me, okay? All right, just leave your camera on. All right, So in the second level then, this is lithium. We've just got one electron there. One element in this S sublevel, one element in the second row. So we just need one of these arrows. Okay? So that's the orbital notation for lithium. All right? And let's go over and look at fluorine now and do the orbital notation for fluorine. So fluorine is going to have all those electrons for the same reason. But now to get to fluorine over here, we're going to have to fill up S in the second row. So I need a second electron there. And to get over to fluorine, I've got to go 1, 2, 3, 4, 5 electrons into the D sublevel section. We can put up to 6. And once we have the D sublevel section open, all those orbitals are actually there. So you have to draw out all those orbitals. And then we're going to put those 5 electrons we need in this subsection. Okay. All right. So those are the orbital notations. Now, in order for lithium and fluorine to be as stable as they can be, and all of nature is seeking stability. There's a thermodynamic law of the universe. I think it's the second law, which says the universe is tending toward entropy. Well, entropy is a more stable state. I can look it up and tell you if it's the second or not, but I think it's the second. Sometimes they number it weird because the first law is numbered the 0th, and the second law is numbered the 1st. So the second law is called the first. So I know that's kind of weird, but that's the way it's done in physics. But this seeking stability means that we want to have that state with 8 electrons in the outermost energy level for larger atoms. And remember, we talked about, well, if you were in class yesterday, you would have heard this. So if you're the A group, you know this, that the smaller elements only want 2. So hydrogen and helium, they only have a one energy level, and then it's only an S sublevel in the first level, and you can only put 2 electrons in there. So for hydrogen and helium, the stable state is 2 electrons. Okay, so lithium is kind of like that. What lithium is going to do or seek to do, and I hesitate to use that word seek because it implies that lithium is alive. There's only things that are alive can seek things, but it becomes more stable by having just 2 electrons and only in that first level, and that would be a full outer energy level. Okay, and that would meet what's called the octet rule. The octet rule says, and we said this in class for the A group, when you watch the video on Tuesday, you're done. Okay, when you watch the video on Tuesday, you hit submit at the end, right? Okay. When you watch the video on Tuesday, you will hear me talk about the octet rule and what it means. Essentially, most elements want to have 8 electrons, and again, that's personifying elements, and they're not really people, or they're not really alive, but they seek to have, again, that's another problematic term, but we don't have good terms for this, but they become more stable. So a chemist would understand if I say that they become more stable. But for students who are just learning about this stuff, saying more stable doesn't make as much sense as saying they want to. Okay, so that's why I use that term, try and help you understand. So lithium, in this case, wants to become more stable, and it can become more stable by having a full outer energy level. If we get rid of that 1 electron, it becomes more stable. It becomes the same orbital notation as helium, and helium is a stable element. That's why helium is a noble gas. These noble gases tend to not want to bond with anything. You can't get helium to bond with anything. You can't get neon to bond with anything. You can't get argon to bond with anything. And only with working really hard at it can you get krypton and xenon to bond with something. And that's only because they have D sublevels. That's a whole other story for another time. In fact, we won't even get into it in this class. So it's a college level class. So what's going to happen is this 1 electron wants to leave. Well, as it turns out, fluorine will be more stable by having a full outer energy level with 8 electrons. Right now, it's in the outermost energy level. That's the valence level. That's another term we talked about yesterday that Group A will learn more about when they watch the video on Tuesday, but you can write it down now. These outermost energy level electrons. So for fluorine, 1 is a lower level, and 2, both the S and P, these electrons here in the outermost, the largest energy level in fluorine, those are called the valence electrons, V-A-L-E-N-C-E. So if you're an A group student, you might want to write down what valence means. Valence electrons are those in the highest primary energy level, and the valence level is the highest primary energy level, okay? So the highest primary energy level of lithium is 2, and it's going to lose that. And fluorine, its highest energy level is 2, and it's going to gain an extra electron there through this process. So it's not what really happens. We think about it this way because it's easier to understand by thinking about it this way, that we move this electron over here and put it down in this orbital, okay? All right, I want to redraw lithium now without that electron. So we just have 2 electrons now, okay? Lithium has 3 protons, all right? So 3 protons. And protons have a positive charge. That's why we put that plus sign on the element, on the symbol for protons. It had originally 3 electrons. Now it only has 2, and electrons are negative. Okay? We got 3 protons, 2 electrons. So as far as the number of charges in this lithium, I've got 3 positive charges and 2 negative charges. And that gives me an overall charge for this thing now of a 1 positive. Okay? Does that make sense to everybody? And that looks like, give me a thumbs up here, guys, so I know you understand what I'm talking about. Thumbs up, thumbs up, thumbs up, thumbs up. Connor, thumbs up for me. There you go, good. All right. So we can't just leave that written there as lithium because it's not lithium anymore. Now it's a lithium ion, and we have to show its charge. So we'll put that plus charge as a superscript on that lithium symbol. Okay? Well, the same sort of thing happens with fluorine. Okay? So here's fluorine, the way that we've changed it around now. So all those electrons that it had originally, it still has. But we've added 1 extra electron over here. Okay? So this number at the top of the cell in the periodic table means that fluorine has 9 protons. It originally had 9 electrons. So an atom of fluorine like this has the same number of electrons as protons, but we just added an electron. So it now has 10 electrons. Okay? That means we have in that fluorine structure, we've got 9 positive charges and 10 negative charges. So what's the overall charge then of fluorine? How about we start with Will? What's the overall charge now of that fluorine? What do you think? Your microphone's on mute. You got to open. Okay, go ahead.
All right.
That's the math right there. What's the answer?
Would it be 1 negative?
You got it. One negative. Okay. That's not really hard. The math's easy. Okay. I'm trying to explain this in a way that comes out to be easy. We're moving around electrons and doing orbital rotation. That's all kind of new, but the math should be, fairly easy. So don't make the parts that are easy hard. Okay. Do the easy stuff the easy way. All right. So we're going to put a negative charge on that fluorine because it's not a fluorine anymore. In fact, it's not even called fluorine anymore. It's now called, oh, that's not even the right spelling. Fluoride. That's called fluoride. Okay. So negative ions are monoatomic ions. We'll learn later what monoatomic means. This atom is fluorine. The ion is fluoride. Okay, so negatively charged monoatomic ions have an IDE ending. You might want to write that down. Negatively charged monoatomic ions, negatively, we spell that just like negative with ITY. Well, I'll spell it for you. Negatively charged monoatomic ions, mono meaning one, monoatomic ions. And ions are spelled IONS. Okay, and ions are charged molecular or atomic particles. Ions are charged molecular sized or atomic sized particles. So negatively charged monoatomic ions have an IDE, maybe we'll call it a suffix. We're being consistent with your English teachers, okay? All right. Let's take a look about what happens then when it's not quite so simple as this. All right, we'll find something that's not quite so simple then. Let's look at magnesium and combine it with chlorine over here. Okay, magnesium is 12, chlorine 17. Okay. So magnesium is in the third row, which we call a third period of the periodic table. So it has electrons in the first, second, third primary energy level. Okay. So the first level is full. The second level, all these S&P orbitals, they're going to be completely full. In fact, even that red electron I have in this symbol, this drawing here, that's going to be in magnesium. And then after we fill up the second level, we're going to go to the third level to do 2 electrons in the S sublevel section. So this is in the third level. We'll call that 3, the third period up here, or the third primary level up here. Okay, 3S, and we got 2 electrons there. Okay, and we're going to see what happens when we try to combine that with chlorine. Now, chlorine's in the same row, so it's the same period, and it's also going to have electrons in that same third primary energy level. But now, with chlorine, we've got 1, 2, 3, 4, 5 electrons in that P subsection. So all of 2 is full, so 2S and 2P, those are full. And then 3s, we had 3s full here with magnesium. We're going through that section. Okay, so we went through the S sublevel section to get over here where chlorine is. Now we're in the P section of the third level. And we need 5, we said, electrons. 1, 2, 3, and according to the Pauli exclusion principle, you have to put 1 electron in each orbital before you can pair anything up. So that's 4 and 5 there. Okay? All right. So chlorine would be more stable, just like fluorine is, by putting an extra electron down here in this last orbital. That would give it a full outer energy level. In fact, the more sublevels that are full provide some extra stability. Okay, so magnesium is a bit more stable than sodium is, because sodium just has 1 electron there. We don't get into that too much in high school. We just stick with that octet rule stuff, okay? So what would make magnesium even more stable is if I could remove those 2 electrons and leave myself with this full outer energy level. Do you understand what I'm saying? I'm leaving myself with a full 2-second outer energy level. Everybody give me a thumbs up to let me know you understand. If you don't, shake your head no, or give me a thumbs down or something. Help me out here. Okay? Okay? All right, good. So in this case, I can remove 1 of these electrons. Let's say I'm going to remove this one here just because it's easier to draw it when I do that, okay, and put it over there. Well, that takes care of chlorine, but magnesium still has an electron up here in this third level. And so it's not really more stable this way. I've got to get rid of that second electron in the third level to leave myself with a full second energy level. So what to do that, I need a second chlorine. Nope, I don't want to put that last one in there because I'm move an electron down there. I don't want to do that yet anyway. Okay, so I want to now move this electron right here over here into that orbital. Okay? The result, all this becomes then magnesium has 2 less electrons. Oh, 3s is gone. I don't need 3. I could leave it blank, but I usually just leave that completely gone. Okay, that one's gone. And because I got rid of 2 electrons, so magnesium had 12 protons, or has 12 protons. It had 12 electrons, and the positive and negative charges balanced out. But now I've got 12 protons and 10 electrons because I got rid of 2 of them. So 12 protons and 10 electrons. Since protons are positive, that means I have 12 positive charges. And now I have 10 negative charges. Okay, so Lauren, what's the overall charge now on this magnesium?
Positive.
Actually, 2 positive, because I've got two more positive, right? That makes sense? Yes or no? It makes sense.
Yes, it does.
Okay, good. So it's 2 positive. So when I put the charge on magnesium, I can't just put a positive like I did with lithium. I've got to say that's 2 positive. Okay? That makes sense to everybody. Hit thumbs up if it is, thumbs down if it doesn't. Ben, you there? Okay, I sort of see you. You got a really dark part of the screen and a really light part of the screen, and it makes it kind of hard for me to tell what's on there. Okay, so it'd be better if either you were completely in the window or completely off the window, one or the other. All right. So then chlorines, then I've got to have 2 of these chlorines, each with an extra electron. So we're putting that extra electron on here. Okay, Guillermo, chlorine had before and still has 17 protons. The chlorine originally had 17 electrons. 17 protons. But now this chlorine has an extra electron. So instead of 17, it's got 18 electrons. So what's its charge going to be?
-1.
You got it. So it's a one negative. Now, just for the record here, so we're clear on this, notice I'm not putting negative in front. These are not numbers on a number line, they're charges. So the charges go behind the number. A negative number on a number line the negative goes in front of the number, okay? That's why I put it behind it, okay? So we're going to put a negative on both of these, okay? Everybody clear? So it's reasonable to just write a 2 in front of this rather than write this twice eventually. Okay, we'll get to the point where you can figure it out without having to write chlorine twice. That makes sense? You write it one time as long as you show there are 2 of them and it's clear. All right. So basically you kind of got to keep going back and forth between the positive and negative parts until you get the number of positive charges equal the number of negative charges. I've got overall 2 different 1 negative particles here. That adds up to 2 negative overall, and that balances out this 2 positive over here. So if you understand what I just said, give me a thumbs up. If you don't understand, give me a thumbs down so I can go back over this. Okay, I don't see, okay. Quentin, I don't see you at all. Ben, I didn't see your hand, thumbs up or down. Okay, good. So if I were going to write the formula then for this, okay, I would have a lithium with a 1 positive charge and a fluorine with a 1 negative charge.
Sorry. Why don't we just say yes?
You can do that, I guess, but here's the problem. I was asking for the thumbs up because not everybody does that. The difficulty is if everybody's saying yes, sir, in this format, I can't tell who's saying yes, sir. Okay? So it'd be better for me right now, and since we're doing this distance learning thing, that you give me a thumbs up, okay?
Okay.
All right. So that's a 1 positive plus a 1 negative. That gives me a 0 charge overall, and that's more stable. So everything about this process creates increased stability. The fact that we move electrons around so that you have a full outer energy level, move electrons into fluorine here, have a full outer energy level, and because you put these charged particles together to get a 0 charge. Both of those together create a more stable system. And that's desirable. Again, that's a personification thing, but that's desired. Okay? So the actual formula is this, LIF. Okay? For the magnesium and chlorine system, we've got a magnesium with a 2+ charge, and we're adding that to a fluorine, or chlorine rather, we get chlorine, each of those having a 1 negative charge, but there are 2 of them. So we still have a 2 positive and a 2 negative. And that's stabilizing, that's a stabilizing effect. And so the formula this time is MgCl subscript 2. So we're showing more than one atom bonded to another. You use a subscript for that. If you're showing 2 separate particles, you use a coefficient for that. Okay? So everybody understands the terms coefficients and subscripts? Thumbs up, thumbs down? Okay? Okay, good. So that's how we're going to use them. It's not the way that you're used to using them in math, because in math, a subscript means something entirely different. But in chemistry, a subscript after a chemical symbol means there are 2 of them that are bonded to themselves or to something else. Okay, there's bonding going on. All right? Okay, so let's give you a chance to practice now. I want you to put together, this system only works when we're talking about single atoms. So there's single atom, starting with a single atom, single atom, single atom. We're putting together single atoms, okay? We'll talk about polyatomic ions at a later time. I want you to put together let's say you put together sodium and sulfur. All right? So I want you to, in doing this, I want you to show me the orbital notation, show me how the electrons move around, and then show me the charges that result, and then show me how you put together the formula to get a balance formula here and here, okay? So you don't have to show me all of this stuff necessarily. That would be something you use to help you, but you do want to show me this math I'm pointing to here and this math I'm pointing to here. This is a kind of a balanced chemical equation. This is a balanced chemical equation, okay? Everybody understand? All right, so I'm going to give you a chance to do that, and then we'll come back together and we'll have you guys help me out by telling me what to write down, okay? Or at least in part, we'll do that. Looks like Guillermo's done. If you need more time, raise your hand so I know you need more time. Okay, got a couple people that need more time. All right, and it's okay to be wrong, guys. I hope you kind of are getting that you're still learning, even when your first chance at trying this stuff is wrong. It's like when you're riding a bicycle for the first time. You're going to fall down sometimes and sometimes skin your knee. Of course, nowadays they have knee pads. Back when I was learning to ride a bicycle, nobody knew what a knee pad was. Bicycle helmets, nobody knew what that was either. So luckily you guys might have had those. I'm careful with my grandkids when they're riding bicycles for the first time that they wear particularly helmets, because those head injuries can cause some permanent problems. I know that's a completely different subject, but you're going to make mistakes here. It's just expected. But right now, what we're doing is giving you a bicycle helmet in a sense, because you're protected. It's not like it's going to affect your grade if you're wrong, but you figure out why you're wrong as you practice this stuff. All right. If you still need more time, raise your hand again, please. Looks like everybody's ready. Can anybody figure out why I put this on the screen? Have you ever seen this before? Anybody? Okay. That's there's a TV network or a cable network called Ion Television. And I'm not sure where they got the name Ion from before, but their slogan is a chemistry joke. Positively entertaining. Ions, half of them anyway, are positive. Positively entertaining. All right. Well, nobody seems to be impressed, but I think it's kind of funny. I laughed when I first saw that, but that's just me. All right. If everybody's ready to see the way it should be done, let's reveal that. Okay. Compare your work to what I have here. I can make it a little bit bigger for you. All right. Does anybody have any questions about this and how this is done? Do you need me to leave this up on the screen a little bit longer? Okay. If you didn't get it right, and now you better understand, that's great. If you didn't get it right and you're still confused, it would be really good if you'd ask me a question about that now. If there's something about this you don't understand.
I have a question about.
Go ahead.
On sulfur, the 3P,
Mm-hmm.
there's like two up arrows on the last two boxes.
Right.
Like, aren't there supposed to be downward arrows?
Well, there will be once you put electrons in there down here. Okay.
Oh, okay.
But sulfur originally had just 4 electrons, one, two, three, four electrons in that p sublevel. Okay. So we got 2 here, 2 in this box, and 1 in this box, 1 in this box. That's 4 in the p sublevel. Okay. So when we write it the first time, you write it the way you were taught in Unit 2. Okay. That's the ground state electron configuration, or orbital notation rather. Then once we move the electrons there, the second drawing here shows what happens after they're moved. It's kind of like a comic book. Okay. And I know kids don't read comic books as much as I did when I was your age, but that's becoming kind of an art form. You know, you actually pay some big money for some classic comic books these days. I used to have a first edition of a Marvel comic book that I didn't keep. I don't know whatever happened to it. My mother finally threw it away. If I still had that, man, it'd be worth big bucks. But anyway, I had some first editions of Spider-Man comic books. Who knows whatever happened to them? That's sad. Of course, they weren't mint condition because I read them, you know. But if you have a first edition comic book of a popular comic book series that's not even been opened up, it's still in the original package, boy, that can be worth some money. But that's just the way it is. All right, that's beside the point. The point is that we're building this like a comic book, okay, where this is like one panel going to the second panel, all right? And I wish that made more sense to you. If you don't read comic books, you don't kind of know, all right? But this just shows how we go from stage one to stage 2, okay? That makes sense? If you're in drama, it's kind of like blocking. All right. If you know what blocking is, if you're getting any plays or whatever, you talk about where you're supposed to be for this at this point in the scene, and then where you're supposed to be in the next part of the scene, and how you get from A to B. So it's kind of like that. Okay, I'm trying to help you figure that out if I can. All right. Any other? That's a very good question. Thank you. Any other questions? Everybody's good? All right, then. What I'm going to do then is assign you a homework problem, okay? And I'm going to give you the remainder of the time we have in this class to work on it. How about you as homework? And I won't check this till after the test. I'll have to figure out when I want to actually make it due. But the homework assignment, let's see. How about we put together lithium and phosphorus. Okay.